Hello. Okay, good morning, people. So, just let me revise a bit of it that we were looking at in the last class, and then we can continue from there. So, we know the structure of the nephron had two main parts, renal corpuscle and renal tubule. Renal corpuscle has glomerulus and Bowman's capsule, and the renal tubule as such has PCT, proximal convoluted tubule, because it's in proximity to the this renal corpuscle. Convolution was the folding. So PCT. Henle's loop, first part is the descending limb and then the ascending limb, and then is the part which is called as distal convoluted tubule. Again, distal because it is farther from the renal corpuscle. And collecting duct is actually a collecting portion of all the nephrons. So as such, you don't write it as a part of nephron, but it is in continuation to nephron, right? But if specifically being asked what are the parts of the nephron, then you can mention collecting duct as well. But write there specifically that it is not a part of nephron, but it is in continuation, because in the diagram, if you look at this part, it is like the kind of main pipeline or tubular structure which is collecting from all the nephrons. So it is not part of one nephron, rather it is part of many nephrons there. So these were the different structures that we had looked at. Also, we had specifically looked at what is the specific functional aspect of the PCT, in which the maximum reabsorption takes place. And I had also explained why it is maximum reabsorption, because whatever has just filtered out from the glomerulus, what we call as glomerular filtrate, that is coming out of glomerulus, that is the capillary network, all of the nutrients and as well as maximum amount of water will be out from the glomerulus. That's what is glomerulus, and that will be entering into the proximal convoluted tubule. So obviously the PCT will have maximum amount of water, maximum amount of the solutes, and that is where the maximum reabsorption can also take place. So that is where the reabsorption phase happen to the greater extent. It's a simpler phenomena. Wherever it is available in higher concentration, obviously that is the place higher reabsorption can happen as well, and that place is PCT. And it is this glucose, protein, amino acid, and so on, that we had looked at in terms of proximal convoluted tubule. Also, one of the fact that we had looked at, that the maintenance of the electrolyte balance as well as acid base balance in terms of body fluid happens in the PCT to a greater extent, because it will secrete different ions like hydrogen, ammonia, potassium, and so on, and in exchange with bicarbonate. So that way, 1 minute. Yeah, okay, happen. So that way this bicarbonate is also present. So that way, whether it wants it to be acidic or basic, respective ions can be secreted or they can be retained or reabsorbed. So depending on that, the balance of these pH as well as electrolyte is also balanced. Meher, I can't hear you if you are trying to speak. So it would be best that you keep yourself muted for the time, because there is background noise coming. Yeah, then the second portion that we had seen was the Henle's loop, where it had descending and ascending limb. Descending was the first part which is going down into the medulla, and it is permeable to water. That means water is allowed to go out and then it enters into the blood, but it is impermeable to electrolyte. That means the electrolytes or solutes, they are not allowed to pass through the descending limb. And the ascending limb is exactly opposite, where it is permeable to electrolyte, but it is not permeable to water. So first, whatever water is there coming from PCT will be absorbed. solute will stay as it is, and in the ascending limb, solute can get reabsorbed into the blood, and then the water can stay as it is in that ascending limb. And whenever we say absorbed or secreted, it means they are getting back into the blood. I hope you are able to imagine that situation. From glomerulus, from blood, it came into the nephron. So from nephron, if it is absorbed or reabsorbed or secreted, it is going back into the blood. So that way, and that is when the vasa recta, that is the network of capillaries around the nephron, was present. Now, coming to the new part of the nephron, that is distal convoluted tubule. So from here, we will continue with the today's class. So in DCT, which is the last part of the nephron, and like I mentioned, the collecting duct is not usually considered as part of one nephron, rather it is part of collective nephrons. So it connects and empties its content into the collecting duct that lines the medullary pyramids. So those conical shaped bodies within the kidneys, on their edges, they will have collecting ducts into which the distal convoluted tubule will empty its content. So the collecting ducts contents from the different neurons, they will fuse together, and as they enter the papillae of the renal medulla. So I will have to go to this diagram. So this is the part of DCT, like whatever is higher diameter here, this part which is connecting to this collecting duct. So all of this content will be entering into the collecting duct from DCT, and from there it will be kind of here. So it will be emptied into this portion, right? That is the calyx region, or what we call as renal pelvis. This empty portion within the kidney, that is renal pelvis, and through the papilla, that is the tip of this medullary pyramid, it will be entering into the renal pelvis. So that way there will be collecting ducts all emptying into this renal pelvis area. Where is it? Yeah. So similar to PCT, that is proximal convoluted tubule, DCT also secretes the ions such as hydrogen, potassium, ammonia, and reabsorbing the bicarbonate. And why does it do that? Because if the PCT is not able to maintain the acid or electrolyte balance, acid base or electrolyte balance, then it can come to DCT to act more efficiently, and from there the reabsorption of these ions or secretion of certain ions can happen based on whether the urine is acidic, basic, or whatsoever is the situation. So depending on that, just like PCT, the distal convoluted tubule also functions to maintain the balance and the electrolyte balance, acid base balance as well as the electrolyte balance. But the major function goes to PCT. Conditional reabsorption, that is as and when required, reabsorption of the sodium ions and water takes place in DCT. Otherwise, whatever reabsorption had to happen has already happened in the first few parts, that is first being the PCT, proximal convoluted tubule, and the second being the ascending limb of the Henle's loop. That's where the reabsorption of electrolytes would have happened. But let's say if at all there is more and more requirement of the sodium and water, that's when the DCT also allows the conditional reabsorption, if it is a condition. And thus it also maintains the pH and the sodium potassium level within the blood. So that is the whole function of the distal convoluted tubule. And the last part, that is the collecting duct, which is a long straight tubes where H plus and potassium ion, that is hydrogen and potassium ion, they are secreted to maintain the electrolyte balance of the blood. Secreted again back into the blood. So if the blood has less amount of H plus ion, these will be secreted from the collected urine, and they will go into the blood. If it is not required, they will pass out into the urinary bladder. So this is also the region where maximum reabsorption of water takes place to produce the concentrated urine. So like especially during night situation, you must have noticed in the morning, that is the first urination of the day, the urine is mostly concentrated. And the reason being, because most of the water has been reabsorbed over the night time, because the kidney functions involuntarily there. That is, the brain takes over it during the sleep time. And that is where the maximum reabsorption also takes place of the water. So urine becomes more and more concentrated. But even during normal course of time, it's not just night, but even during the normal course of time, if there is more water in the collecting duct, that will also be reabsorbed if the body is in need of that water. If body has sufficient water, this reabsorption does not happen. That also you need to like pay attention. So these are the different parts of the nephron. Now, does anyone have any question? Okay, so just to mention two different types of nephrons, depending on where they are present. One is cortical nephron, another one is juxtamedullary nephron. Cortical nephron, they are present within the cortex, and maximum portion of these nephrons, that is almost 80% of this total nephron, is present within the cortex of the kidney. While the juxtamedullary ones, these have long loops, one that we had seen, loop of Henle extended into the medulla. That is, half of them is in cortex, half of them is in medulla. That is juxtamedullary. The one which we had seen in the diagram was actually juxtamedullary nephron. And the cortical nephron, maximum part of the nephron, they are in the cortex itself. And the juxtamedullary nephron, they are just 20% of the total nephron. So that is just two types you need to know. Again, there was a very specific question asked in juxtamedullary nephron, that where is the cortex? Which part of this nephron is present in the cortex of the juxtamedullary nephron? And then you have to specifically write glomerular, PCT, DCT, and so on. So that way, these structures will be present in these respective like part of the kidney. Then blood supply to kidney, this part we had seen in like detail earlier itself, so I'm not going to touch upon this. But what you need to know here is, you know what glomerulus is, which is the capillary network. You know what afferent and efferent arterioles are. And there is just one thing that maybe I would have missed, is the secondary capillary network called as vasa recta. So let me show you that in the diagram. So this is the part of the glomerulus, right? This blood capillary network. So after efferent arteriole, after a little distance, it again bifurcates into several branches so that it covers PCT, DCT, and Henle's loop. You can see there is one capillary network here. Now it is simplified version, obviously. So you may not see it like a capillary network, but at least these three branches, again they are merging, again three branches, again they are merging. So there can be more branches as well. So what they mean to say is, this capillary network which is after efferent, so whatever is being reabsorbed from these Henle's loop, PCT and DCT, goes into these blood vessels. And this network of capillaries is called as vasa recta. So that is the point that probably I have not covered earlier. But the rest of all these points we have already discussed enough, in terms of where does the blood come, what does happen to it, where does it go further, and so on. So that you can read it on your own. And this vasa recta is the additional part, which is the secondary capillary network apart from glomerulus. Yes.
How many approximately nephrons are present in the like overall total donor kidneys?
Sorry, how many?
Total number of nephrons in both the kidneys. Like how many approximately?
No, I couldn't hear you. Total number of what?
Nephrons.
Are present where?
Like in the body, like total.
So within the body, you mean?
Yeah,
Within,
how many? Yeah, how many approximately?
you missed that point clearly. Where is that? Millions of nephrons, that's what the line says, in each kidney. Somewhere here. Or
They're
maybe.
microscopic.
Sorry?
They're microscopic structures.
Yeah. And we, like I also mentioned that the 3 to 4 centimeter, that is the size. Where is that part? Kidneys, nephron. Here it is.
Yeah, yeah.
About millions of nephron in each human kidney, and the length is 3.5 to 5.5 centimeter long,
Okay, okay.
and millions can be anything. Okay, now this is the last part, rather the second last part, which is the production of urine, which is nothing but the mechanism of urine production. How is the urine getting formed? Again, in brief, we have seen this process, but still we need to go over it once as a whole mechanism. So there are three main steps, what we know as ultrafiltration, or it is also called as glomerular filtration. Reabsorption, it is also called as selective reabsorption, and tubular secretion. The first step, now we have already discussed that glomerulus, from the afferent to efferent, there is a diameter difference, and that is why the hydrostatic pressure is built up. That is high pressure, which causes liquid part of the blood to filter out. That is the plasma part, right?
So, sorry to interrupt. What did you say that ultrafiltration is also called?
Sorry,
You said that ultrafiltration is also known as something.
glomerular filtration.
Oh, okay.
Yeah, so that hydrostatic pressure is being built up, which causes the fluid part of the blood to filter out from the glomerulus and it enters into Bowman's capsule. And this specific type of glomerular filtration, with or under extraordinary force of hydrostatic pressure, is called as ultrafiltration. Sorry, again, in the case of this filtrate that is coming out, to remind you, that is called as glomerular filtrate, because it is coming out of glomerulus, and it contains all the components, soluble components, organic, inorganic, including glucose, urea, amino acid, and so on. What it does not contain is only the blood cells and large molecules from the blood. Rest everything it can contain. uh, yeah, and that is what is being mentioned in the last part, this part. Now whatever, it consists of water, urea, salt, glucose, and other plasma solutes, and that is called as glomerular filter. Now whatever thicker part of the blood is left behind, including blood cells, proteins, and other large molecules, because most of the liquid part as well as most of the solute have gone into the glomerulus, sorry, into the Bowman's capsule. So whatever is remaining in the efferent arteriole, that is exiting arteriole, will be a thicker blood, not literally thick in consistency, but there will be less blood volume comparatively than what was coming or incoming into the afferent. So that one, uh, uh, they are carried forward, that thicker part of the blood will be carried forward through the efferent arteriole into the vasa recta network, so that whenever reabsorption happens, that is the next step, all of it can be back into the blood. So reabsorption, that is the second step. So glomerular filtrate, that is the thicker part of the blood, the whatever is incoming into the Bowman's capsule, that will enter into the renal tubule, is not urine. So we usually have a misconception that whatever has filtered out from the glomerulus, that, yeah, as a glomerular filtrate, comes as it is to become urine, but that is not the case. It gets reabsorbed to quite a lot of extent. That's what we had seen earlier, and then it becomes urine. So that is what the first point says: glomerular filtrate is not urine. It is extremely dilute solution containing lot of useful substances, like for example glucose, some salt, electrolytes, and so on. And these needs to be reabsorbed. And that whole process of reabsorption is called as selective reabsorption, because it selectively picks up the molecules based on what is the need of the body. If it is not required, then they are obviously excreted into the urine part. So that is this selective reabsorption process. And the third stage of the tubular secretion, again, whatever is excess into the blood, that is secreted back into the urine or secreted back into the what we call as a nephron. So certain substances like potassium and large number of foreign chemicals like medicines that we take, that's what they are talking of, the foreign chemicals, including the drugs like penicillin and so on. They are passed into the forming urine, that is not completely formed, but so the forming urine in the DCT. So all that tubular secretion happens in the distal convoluted tubule. And this passage involves the activity of the cells of the tubular walls of the DCT, because those cells, they will allow certain molecules to cross that barrier of the tube, or they will allow certain molecules to come inside the tube. So that is why it is involving the activity of this tubular structure of the DCT, and that's why it is called as tubular secretion. And now whatever the filtrate is left after reabsorption as well as the tubular secretion, that is what is called as urine. And all these steps in the urine production, they need energy, because they always happens against the concentration gradient, because it's selective process, and hence the oxygen demand, ultimately the energy demand for this for the kidney is much higher than that of muscles. So that is just one state of fact here. So that is the whole mechanism of the production of urine. Again, I hope that this part was clear to you. If at all you have question, you can ask. If not, I will move to the urine excretion, which is the smallest component, which nothing but we already know, that the final urine passes into collecting duct. From there, it will enter into the pelvis. Then it will enter into the ureter and bladder, and through the ureteral peristalsis, due to the gravity, it will be expelled out of the body through the urethra structure. That is by the relaxation of the sphincter muscles at the base of the urethra, and that process is called as micturition or urine excretion process. So that is the last part of this urine production. This diagram kind of is a summary for all of these processes. This is just for your reference, so that you can at one go you can revise what molecules are coming in, what molecules are going out, and so on, and at what stage. So you can revise this on your own. I'm not going to talk about it because we have already discussed enough. Just one point I must say here. You can see this is yellow part is the nephron part structure, and this tube, blood vessel or the capillary, is coming very close to the nephron structure. That is how in reality this situation are. So whatever is getting reabsorbed from the nephron goes into the blood, or whatever is secreted from the blood goes into the nephron. So that way they have to lie very close to each other, so that that exchange of material or solute can happen, or even of the water can happen. The last part, the composition or the characteristics of urine, which talks of, again, you would know most of the basic characteristics. It is pale yellow in color, and that color is due to the urochrome, which is the breakdown product of the hemoglobin, and that is coming from the wear and tear of RBCs. So that is the whole chain of sequence. And this color may vary with the diet. So if you are drinking lot of water, or if you are drinking less of water, either of cases the color will change. If you are undergoing certain infection, the color would change a bit, because that will give turbid like color, not turbid color, turbid consistency to the urine. Volume usually 1 to 1.5 liters per day is expelled, but again this depends on the how much amount of water you drink. pH usually slightly acidic. Again, it is dependent on what is the diet content. So more protein will make it more acidic, or more vegetable diet will make it more alkaline. So depending on the diet content, the pH can slightly vary, but it does not go drastically acidic or drastically basic. It's always around the neutral pH or slightly acidic pH. Odor, In general, urine does not smell, but upon storage, it smells like ammonia because of the bacterial activity. So bacteria will degrade urea, and that urea will get converted into ammonia, and that is what we get as a smell. So the moment the washrooms or urinals they stink, that is mainly because of this ammonia content and not because of the urine as such directly. And that's where the bacterial activity is also maximum. Specific gravity. Specific gravity is one of the physicochemical property of the urine, which compares the density of the material with respect to that of water. So obviously urine has water along with the solute, and that density compared with plain water or like what we call as pure water. So that specific gravity is 1.003, which is obviously due to the presence of solute in the urine component. Uh, then there was one more parameter, which is taste. Now, taste of urine is salty and sometimes sweet, but no one goes and tests the urine. That is like quite obvious and creepy also at the same time. But that's why I have not included. But just in case, if at all something like that comes up, you know what to write. Constituents of urine, almost 95 to 98% is water, and the remaining percent is of the solute, which includes urea, creatinine, uric acid being the major ones, and sodium chloride, potassium chloride, ammonia, and other substances. You are not supposed to remember these numbers of the subcomponents, but you surely need to remember the names of these constituents. A maximum percentage is of the urea because that's what all the nitrogenous waste gets converted into, and some amount gets converted into uric acid as well as the creatinine component. There are various situations that are related to the urine, what we know as hematuria, which means presence of blood or blood cells in the urine. Now, this is usually whenever we have certain kidney infection or bladder infection or urethral infection in any of these cases, or even the kidney stone, where the blood cells they are exposed to the innermost part, and those blood cells they come out in urine. That situation is called as hematuria. Diabetes mellitus, which is again everyone would know what diabetes is, which is excess of glucose within the body, within the blood, and obviously because of that there will be excess of glucose in the urine as well. That specific situation is diabetes mellitus, and the name to given to you, I guess it is glucosouria, not glycosouria. Maybe I need to check this, but it should be glucosouria because glucose in urine, that's what it literally means. Then albuminuria, due to the high blood pressure. Now, whenever people with hypertension or people with high blood pressure, they allow the increased permeability of the Bowman's capsule so that the larger molecules like albumin can also enter into the nephron structure, and then they are entering into the urine. So that situation is called as albuminuria. Bile pigments in urine. Now, due to anemia like situation or hepatitis, which is infection of the liver or liver cirrhosis or jaundice, in any of these situations, the bile pigments can appear into urine. That is another situation related to the urine. And this part, again, I'm not too sure if it is excluded completely from the syllabus because the syllabus document does not mention of this, but I feel it is very much part of the syllabus. Knowing the production of urine is part of the syllabus, so that's why I have included. So please do not, and that is the reason I have not written extra here. So please consider this as a part of syllabus, because if at all question comes, because osmoregulation is very important process, and they cannot remove this topic from the syllabus, keeping the production of urine in the syllabus. So that's why I have kept it as it is. A very small topic, that is regulation of urine output. it is usually done by the the pituitary gland, which secretes anti-diuretic hormone. Now, diuresis is the process where the increased production of urine happens. That is diuresis. So anti-diuresis is decreased production of urine. So that is what is done by the pituitary gland. So anti-diuretic hormone, if it is secreted, that means production of urine is reduced. And if ADH is not secreted, that means urine production is increased. So that's how it controls the urine output from the body. There are drugs or medicines which we simply call as diuretics, and there are natural diuretics as well. Like for example, after drinking tea or coffee, you feel like peeing or urinating at times, and the reason being because they are acting as a diuretic molecule. Similarly is the case with the alcohol as well. More drinking of the alcohol can cause diuresis, and that is one of the reason, especially for the kidney stone people, it is recommended that they drink some amount of beer, because it's more volume of liquid, more urination can happen. So those kidney stone, they can pass out in the urine easily. So that is the diuretics compound. Gout is a specific situation where the uric acid deposition happens. Now, uric acid is very slightly soluble in water, and because it's slightly soluble, the moment it is present within the urine, and if the concentration increases, it tends to crystallize, and then it will start crystallizing after kidney. It will start crystallizing in joints as well. That's where the deposition happens. So next to your ankle, because of the gravity, obviously whole of the blood flows through the leg structure quite often, and because of that deposition and also of the gravity, the uric acid keeps depositing on the ankle, next to the ankle joint, and that is where the gout is very predominantly observed. That is the uric acid deposition at joint places. Then osmoregulation, we know what osmotic pressure is from earlier chapters. That is maintenance of the fluid and electrolyte balance, or the solute and solvent balance. That is maintenance of the tonicity or osmotic balance and so on. So kidney, while removing the water along with urea from the blood, also regulates the composition of water and salt from the blood to the urine, and that particular function is called as osmoregulation. Because like I showed you this diagram, where the capillary network is very close to nephron, and they keep on exchanging. Whatever is not required will go in urine, whatever is required will stay back into the blood. And also the maintenance of the pH as well as the electrolyte balance is done by this nephron structure, and that particular regulation of osmotic pressure in the blood is called as osmoregulation. And just one small fact, that is the person urinate fewer times in summer than in winter, which is very obvious. In summertime, we urinate less because more water is going out of the body through the sweat or sweating mechanism, that is perspiration. And that is why like we tend to urinate less in summer, and in winter obviously the perspiration is less, so obviously more water should go out through the urine. So that's the end of whole of this story. If anyone has any question, you can ask, otherwise we will stop.
Sachin sir, I just
Yes.
had a question. So basically, the journey of the blood, like the basically transformation of blood to urine, can be summed up as follows: like there's like you have blood which contains the waste material, the nitrogenous bases and whatnot. It enters the nephron.
Right.
It gets separated into like the filtrate, like the glomerular filtrate, and the other part, the filtrate contains the ions and the stuff, and then the rest of the part. Then what happens basically? Like after the filtrate, the glomerular filtrate has been created, then
Nephron structure.
again.
Nephron, yeah, it is already in the nephron, not again. So when the blood is squeezed out or filtered out, that's where it goes into the nephron. Correct?
Okay.
That's what the function of glomerulus is.
Okay, so like, okay, after the glomerular filtrate has been created, then what happens to the, like, then what's the journey to urine? Like,
Glomerular filtrate will enter into the nephron structure.
okay.
From nephron, whatever is required into the blood will be reabsorbed through the wall structure, right? Through the cellular structure. And whatever is not required will be kept within the nephron and that goes out, or whatever from the blood, if it is in excess, again in the process of tubular secretion, it will be secreted within the urine or within the DCT and that goes out as urine.
Okay.
So that is the whole process. And that is when we were looking at this particular structure. Where is it? So this is one for sure where the exchange can happen, and you can consider this as, you know, PCT, DCT, or even Henle's loop. They will have close connection with the blood vessel as well as the part of the nephron. That is true everywhere, and that is when this vasa recta structure was shown. Right? This capillary network is because it is close. Now in diagram it may not be shown close to the nephron, but in reality if you observe this, there are quite few small capillaries. Again in this diagram also they have not shown clearly, but there are quite a few capillaries close to this tubular structure. And once it is going after this, like this blood vessels, right, which is taking the whatever content of the blood, after this it joins to the main vein which goes into the posterior or inferior vena cava. From there it goes to the heart and then the cycle continues. So that is how it functions or it travels.
Okay.